Well, unless you've had your head in the sand for the last couple of weeks, you know that factoring is a major part of algebra. We've been using factoring to help us since back in December to change expressions and then to understand the graphs of parabolas. And now we've been using factoring to actually solve equations and continue to understand the graphs of polynomials. But guess what? There's more factoring. There's more types of factoring. There's more expressions that can be factored. Today is special because we're going to be looking at some certain types of expressions that, well, because they are just special, we can factor them. But we have to have some rules and some more skills. Let's start with a difference of squares. Well, yeah, I mean, why does a difference of squares get all the attention? Honestly, because it's something that was easy. You see, when you have a difference of squares, like 9x squared minus 64, we've learned some time ago that you can always split that up into two binomials that have the same terms, 3x and 3x. 8 and 8. All we need is a plus and a minus sign. So how come squares get all the attentions? Well, not anymore. We're going to look at a different type of difference. Now, by the way, before we do that, we certainly can solve both these expressions. Remember, that's what we're really trying to do. We're trying to solve them. All you have to do is just set them equal to 0 and do a little bit of dividing, or excuse me, adding, subtracting, dividing. But what I really want to focus with you today is a different type of difference. Yeah, difference of cubes. Believe it or not, if you have a difference, a subtraction sign of cubes, that is numbers that are perfect cubes, it actually can factor. You just have to learn the pattern. Well, here's the thing. Like a lot of these problems that are perfect, we have to figure out where the cubes came from. Where did x cubed come from? Where did 125 come from? Well, they came from the items that were cubed. That is, an x was cubed and a 5 was cubed. Notice that this sign right here is the same. But what about this other sort of expression? Is it just going to be another x minus 5 and maybe another x minus 5? No. If we would work that out, we would find out that that doesn't go back to where we started. Instead, it's actually going to be this x that I wrote down, squared. It's going to be this x squared. And it's going to be this minus 5 that I wrote down, squared, with a term in the middle. And the term in the middle is just going to be these two guys that I wrote down multiplied together. Multiplied together. There does have to be a subtraction sign right here, excuse me, and an addition sign, which we will talk about soon as to why. But I just want you to agree with me that if you actually multiplied all of this together, if you actually turned it back into its original form, well, you 100% would end up with what we started with. Now, what I'm doing here is just distributing, and I'm trying to do it kind of quickly, but I want you to realize that we're going to get some things to cancel, like these 5x squareds and like these 25x's. Oh my gosh, we just end up with x cubed minus 125. Well, it's true. We factored it. We factored it. Now, why are we factoring? Quite honestly, so we can solve the equation. I want you to realize that when you factor the problem, when you write it in this new form, you now have the power to be able to solve the equation. You know, like solve this for x equals 5. The only problem is solving this is a little tricky it's ultimately going to require the quadratic formula. But instead of going through the whole quadratic formula, let's talk about this pattern that allowed us to factor a difference of cubes or a sum of cubes. And the pattern is simply that we always think about where these perfect x or a cubed and b cubed came from. They came from a and b. So we think about where they came from. We think about their root officially. And then you always square the number that you wrote down. So if I wrote down a b, I'm going to square that also. And then all I got to do is multiply these together. And when I multiply them together, I get this term in the middle. Now, the one thing you might notice here is that we have certain signs. You see, we have the same sign. And then we end up with the opposite sign. This sign out here is always positive. Let's talk a little bit more about this with the pattern when it's a difference of cubes. Well, it's the same pattern. Again, where did a cubed come from? It came from a. Where did b cubed come from? It came from b. Now, all you have to do is the number you wrote down, it gets squared. The number you wrote down, it gets squared. And then you multiply these together. And when you multiply them together, you get your AB. Look at the signs. Look at the signs. These signs are the same. This one is the opposite. This one is always positive. That idea of the signs fits nicely into a cute little acronym called SOAP. SOAP. And we sort of joke, did you use SOAP? Yes, you use SOAP if you write down the same sign. And then if you write down the opposite sign. And what's true about the last sign? It's always positive. It's always positive. So when you factor a sum or difference of cubes, you're always going to want to use SOAP. Ready to try it? 8x cubed plus 1. It's a sum of cubes. These are both perfect cubes. That's where you want to start. Where did 8x cubed come from? It came from 2x. Officially, it came from 2x being cubed, but we just write down 2x. Where did 1 come from? It came from a 1 being cubed. It came from a 1 being cubed. Now, in this expression, in this parenthesis, what we're going to do is we're going to square what we wrote down. Now, when you square 2x, you get 4x squared, right? You get 4x squared. And then we're going to square the 1. That's still 1. Again, 1 squared is still 1. And then I multiply these together. And that gives me 2x. Did you use SOAP? You did if the first sign is the same. The next sign is the opposite. The opposite. The last sign is always positive. And we just successfully factored that sum of cubes. Sometimes students are ready to try one of these on their own after just seeing well, a few of them. If you're not quite ready, then you're ready to keep listening. You have to recognize that this is a difference of cubes. That means that both these numbers are perfect cubes. Where did x cubed come from? It came from x. Where did 27 come from? Now, if you're having trouble with this, you have to realize that 3 cubed is 3 times 3 times 3. That's 27. So that means that 27 came from a 3. All I got to do now is square each of these. X squared, square the number 9. Yeah, square the number 3. Sorry, that gives you 9. And then you multiply them together. This is the pattern for a difference of cubes. Did you use SOAP? The first sign is always the same. The next sign is always the opposite. The last sign is always positive. And that would be the factoring for that difference of cubes. Now, why are we doing this? Why are we doing this? Well, ultimately so that we can solve an equation. Let's make letter A into an equation. Let's make it equal to 0. So that we can actually, I'll tell you what, let's not do that yet. Hold on a second. Why are we doing this? Well, eventually so we can solve an equation. But I'll tell you what, let's just make sure that we can solve, or excuse me, that we can factor this problem. Okay. Let's factor 2x cubed minus 16x squared. What's the problem? It doesn't look like a cube, does it? That's because you have to always keep in mind that GCF. There's always a GCF that is possible for any problem. Yeah, you got to take out a 2x squared. Now look, that's going to leave you with an x cubed minus 8. Kids, these are perfect. X cubed's perfect, minus 8's perfect. Now what's happening here is I'm rewriting the problem with multiple factors. The 2x squared, don't forget about it. It's still here. But what I'm going to do is I'm going to now factor my cube, my difference of cubes. And that's what's going to end up in these two parentheses. Here, let's change the color so it matches. We'll put them as blue. So where did x cubed come from? It came from x. Where did minus 8 come from? Okay, you have to think, what number do you cube to get 8? That'd be the number 2. Remember, 2 cubed is 2 times 2 times 2. That's equal to 8. Now, once you figure out where these numbers came from, you just want to square the first one. So if I square that, I get x squared. I want to square the number 2. That's going to give me 4. And then you multiply these together, and that gives you negative 2x. Oops. Let's talk about the signs. Remember, the first sign is the same. It's the same. The second sign is the opposite. The last sign is always positive. And so, to fully factor this problem, we end up with actually 3 factors. We get 3 factors that are equal to the original expression. Now, this equation, or excuse me, this expression is an equation. It is equal to 0. So we're going to factor it, but we're going to factor it so that we can eventually solve it. Difference of cubes, right? Difference of cubes. Where did 1 come from? Where did x cubed come from? What happens when you square the number 1? What happens when you square x squared? And what happens when you multiply these together? Now, I don't want you to feel like that this is backwards. It's fine. You can write it with the number first and the x second. You just want to follow and use SOAP. So this sign is the same, this sign is the opposite, and this sign is always positive. I know it feels a little bit kind of backwards, but this is okay. And this is an equation. It's equal to 0. Because it's equal to 0, it's now time to solve each of these factors. Now when you solve, you're looking for the number that will make them equal 0. That one was pretty easy. It's just the number 1. This one right here, that's a trinomial, and it's a quadratic trinomial. Quadratics have to be solved using either factoring or the quadratic formula. You're not going to be able to factor this problem, so we have to use the quadratic formula. That's the opposite of b. Now remember, b is the number in front of x, plus or minus the square root of b squared, minus 4. A is the number in front of x squared. So that's kind of interesting. We have to see the letter A right there. And then C. And C is the number by itself. We end up with some 1s, but still we carefully chose them as A, B, and C. All over 2A. All over 2A, which is 2 times 1. Now, if you work this out, you get 1 minus 4. 1 minus 4, that is the square root of negative 3. So I end up with negative 1 plus or minus the square root of negative 3 over 2. Ooh, what's going on here? Well, it's not that bad. It's just an imaginary number. In fact, it actually just comes out to be negative 1 plus or minus I root 3 over 2. How many numbers technically does this represent? 2, right? 2 roots, technically. How about this root right here? This was 1 root. How many roots do I have in all? 3 roots. Oh yeah, it was supposed to be 3. This was a degree 3 problem. Listen, the fundamental theorem still counts. I know we're on to something else, but we're not on to something else because the fundamental theorem is going to always apply to polynomials. Let's talk about these imaginary answers, just a little bit more information. When you get imaginary answers, they're always going to come in pairs. They're always going to come in pairs, so we're always going to get like a 2 imaginary numbers. That's because these pairs are complex conjugates. Complex conjugates just mean that we're always going to have that plus or minus of the I. So here, I had negative 1 plus or minus I root 3. That's a complex conjugate. So what if I had 3 plus or minus, or 3 plus I, then I would have to be guaranteed to have 3 minus I. Again, you can be guaranteed that it'll always come that way. What if you have 4 minus 7i? You can be sure you'll have 4 plus 7i. That's because imaginary numbers always come in those complex conjugate pairs. That's actually called the complex conjugate theorem. Just kind of in case somebody ever mentions it, I'll probably mention it again, but it's more that you realize that that happens, that that's always true. Sum and difference of cubes. Make sure that you use soap and make sure that you get to know this pattern, the pattern that involves A's and B's and A squareds and B squareds. Let's look at another special type of factoring. And quite honestly, this type of factoring is just like a higher degree factoring. You're going to find out that it uses the same skills that we've already learned. It's just being able to factor when the exponents get a little bigger. X to the fourth minus 6x squared minus 27. Perhaps your first instinct is to sort of say, I can't do this, or how do I do this? Let me help you realize that this is nothing more than just 2 binomials that multiply together. So where did x to the fourth come from? Well, it came from x squared and x squared. How about this minus 27? Can we find 2 numbers that multiply to be negative 27, but add to be negative 6? Wait, sure we can. Negative 9 and positive 3. Those are 2 numbers that multiplied to be negative 27, add to be negative 6. And if you check this, you see that this 3x squared and this negative 9x squared perfectly equals negative 6x squared. And of course, that's the way that this is supposed to work. What do you think about x squared minus 9? It's perfect, right? It's a difference of squares. That means I can actually factor it more. Ah, cool, I can factor that more. How about x squared plus 3? Sorry, that's not a difference of squares. I can't factor it more, but I can write it down. So what do I have here? Well, I have 3 factors that I can solve. Remember, you solve them for their zeros. And as you solve them for their zeros, you're sensitive to the fact that this one, x squared plus 3, when it's equal to 0, is going to give you the square root of a negative number. And when I take the square root, I always get plus or minus, but because it's a negative number, I'm going to get I. And look, I got those plus or minus i's. You're always going to get that. 1, 2, 3, 4. 1, 2, 3, 4 answers. Perfect. This was a degree 4 problem. Can I graph this problem? Sure, I can still graph it. All I have to do is know where the real roots are. The real roots are 3 and negative 3. And if you think about your behavior, you know that the graph has to, because it's got a positive leading coefficient, it has to go up to the right. And because it has an even degree, it's going to have the same behavior on the left. Yeah, this is just going to end up being a graph that passes through 3 and negative 3. And don't forget about the y-intercept. The y-intercept is supposed to match with your equation. These imaginary numbers, they don't show up on the graph, but that's okay. They're still part of the solution set, giving me a total of 4 answers, 4 roots. How about x to the 6 minus 26, x to the 3rd minus 27? I'm not going to give you guys a problem that you have to search far and long for the numbers. I really just want you to see that x to the 6th can come from an x cubed and an x cubed. And since those are both x cubes, I'm going to be able to very nicely find two numbers that multiply to be negative 27 and add to be negative 26. What numbers do that? That's right, negative 27 and positive 1, right? Negative 27 and positive 1 multiply to be negative 27, but add to be negative 26. What do you see? What do you see? I know, it's pretty cool. We have a difference of cubes. We have a sum of cubes. Wait, what does that mean? Well, that means that you can factor them more. You can factor them more using the concepts from the front of the paper. Let's try it. I need a little more space here. Let's factor x cubed minus 27. All you got to do is figure out where the numbers came from. Now remember, 27 came from 3. And if I square x, and if I square 3, and if I multiply them together, and if I use SOAP, so it's the same sign, it's the opposite sign, it's always positive, we got that one factored. Let's factor x cubed plus 1. Let's factor x cubed plus 1. Where did x cubed come from? Where did 1 come from? What happens if you square them? What happens if you multiply them together? Same sign, opposite sign, always positive. Now students, what's happening here is we have just broken down this big old original x to the 6th equation. We just broke that down into these 4 factors. And the whole idea is that each one of these factors is going to produce a solution, or perhaps is going to produce a couple solutions. Now I'm kind of taking the easy way out here. I'm finding the first 2 real solutions. But what about solving this? What you're going to realize is that you can only solve that trinomial using the quadratic formula. And the quadratic formula gives you the opposite of b plus or minus the square root of b squared minus 4ac. Is it all right if I just tell you that that's negative 27 all over 2a? Now, that's going to become negative 3 plus or minus I root 27. And the truth is, the number 27, that is root 27, can be broken down one more step. You can break down 27 to be 9 times 3. And the 9 is going to come out as a 3, but the 3 stays behind. That's a lot, but that's 2 roots. I should say 2 more roots on top of my already roots that I found. But the good news here is I've got 2 more roots. Whoa, where did that big line, scribbly line come from? Let's find the roots for x squared minus x plus 1. Guess what? Quadratic formula. Opposite of b. b is the number -1, so the opposite of b is plus 1. Plus or minus the square root of b squared minus 4ac all over 2a. b squared minus 4ac is -3, so we end up with 1 plus or minus I root 3 over 2. Guess what? 2 more roots. 2 more roots. Where's all my roots? 1, 2, 3, 4, 5, 6. 6 roots. 2 of them are real. 2 of them are real. And those are the 2 that end up on my graph. My graph that's going to have n behavior that is going up to the right, and it's the same to the left. And once again, I have a y-intercept of -27, which makes sense. Now that's not easy, but it is possible to factor things of a higher degree. What we need to do is just kind of break them down into some smaller exponents. And now you're ready to try the homework.